All right, ladies and gentlemen, so today let's talk about exponential functions. We're going to put together everything that we've learned so far in Chapter 7. The two skills that we're working on, the idea of graphing exponential and logarithmic functions showing intercepts and end behavior, and we're going to construct linear and exponential functions, including arithmetic and geometric sequences. So now, we talked before about how we construct those linear functions. Now we're throwing in the idea of exponential functions. So linear, that was our y equals mx plus b, or we had other forms of it. Now we're going to throw in the idea of exponential, which is that geometric sequence. So our one and only vocab term for today is the idea of an exponential function. An exponential function is a function of the form y equals a times b to the power of x, where a is not 0, b is greater than 0, and b is not 1. The two key pieces I see in my equation here are a as my y-intercept, and b is my growth factor. Underline growth factor here. We'll talk a little more about these in a second. But when a is greater than 0 and b is greater than 1, I have exponential growth. When a is greater than 0 and b is between 0 and 1, I have exponential decay. And so that key concept picture in the bottom there shows you what this looks like, my exponential growth and exponential decay. The idea of end behavior tells me what's happening at the ends, at the arrows of my graph. And if I notice on both of these, my x can be any real number. I can go from negative infinity for x all the way to positive infinity for x. But my y values have a limit. As x goes to positive infinity, y also goes to positive infinity. But as x goes to negative infinity, my y values get smaller and smaller and smaller, but they never reach 0. So as x decreases, f of x approaches 0. Well, I have the same sort of thing, but the opposite when I'm talking about decay. As x increases, this time, y approaches 0, but as x decreases, y increases. So I have that invisible line hanging out that my function will never cross. So now let's think about this. We're going to identify exponential growth. So in your notebook, I'd like you to have both of these pieces here. And we're going to start by talking about this first input-output pair. When I look at this here, I know from before that my y-intercept is always going to be the value for y when x is 0. So in this function here, I have a y-intercept of 2. Well, when I look at how my values are changing, I see my x is changing by 1 every time. I want to know how my y values are changing. Well, if I look to go from -4 to -1, I could either multiply by 4 or I could add 3. If I go from -1 to 2, well, if I want to see the same pattern, again, I see that I'm adding 3. So on this one here, I see that I'm adding 3 each time. So what I call my change here, my change, is really a slope or a rate of change of +3 each time. So I know from previous information that this is going to be the function y equals 3x plus 2. I see my y-intercept, and I see my change is a +3 every time I go up by x. But now if I look at my other function here, I have my input-output table. I have a y-intercept of 8. The y-intercept tells me where I cross the y-axis, so it's still 8. But if I look at how my values are changing each time, from 2 to 4, 4 to 8, 8 to 16, 16 to 32, I don't have even increments. It's changing by a different amount every time, but there is a pattern. This is a geometric sequence where every time I'm multiplying by 2. So my change, in this case, is a growth factor. My change is multiplying by 2. And so I can represent that with my exponential function, where y equals my y-intercept multiplied by my rate, or by my growth factor to the power of x. And that would tell me that I'm multiplying by 2 every time. Let's see, I had my change and my y-intercept. Different arrangement here, and if I were to graph these points, if I graph this one here, we'll do a little sketch. It's not going to be perfect. I have 0, 2, 1, 5, 2, 8, -1, -1, -2, -4. I see that I have a nice linear function. If I were to graph these ones here, well, I see that I have 0, 8, 1, 16, 32, 4, 2. I see that exponential curve where I'm approaching 0 at one end and approaching infinity at the other end for x. So now let's do a little thought experiment. This is a real life situation that you could have where you have a string or yarn 1 yard long and you cut it in half. So what we want to do is we want to write a function that models the number of pieces of yarn or a function that tells me about the length of each piece. So first, at stage 0, I have one piece of yarn and it's going to be 1 yard long. But if I take that one piece and I cut it in half, well, now I have 2 pieces, but each of those pieces is going to have a length of 1/2 of a yard. I take those 2 pieces and I cut them in half again. Well, now I have 4 pieces, and each piece has a length of 1/4. Each of my 4 pieces, if I cut them in half again, I now have 8 pieces, but each piece has a length of 1/8. Last step in my table here, I have 16 pieces, and each piece is 1/16 of a yard long. So I want to write a function to model the number of pieces of yarn at stage x for some number x. Well, I know that I'm going to be using that format where y equals a b to the power of x. So if I think about it, at stage 0, when x is 0, y is 1 for my number of pieces. We'll do number of pieces in green here. So I know that it needs to be 0. Well, I see that I have a y-intercept of 1, and I have a change. My change each time, oops, there we go, green. When I go from 1 to 2, well, it doubled. It doubled. It doubled. So my change, my growth factor, is 2. So my equation would look like the number of pieces is equal to that start value times my growth factor of 2 to the power of x. Well, let's check and make sure. If I plug in 0, I get y equals 1 times 2 to the 0. So y equals 1 times 1, y equals 1. I like it. If I plug in 1, when x is 1, I get y equals 1 times 2 to the power of 1. So y equals 1 times 2, I get 2. When I plug in 2, I get 1 times 4. So this is my function to model the number of pieces of yarn at stage x. But now let's think about the length of each piece. When I look at the length of each piece, I'll do this one in blue here, I want to know what my growth factor is. Well, if I see from 1 to 1/2 to 1/4, I'm changing by dividing by 2. But when I'm writing these out, my growth factor needs to be something that I can multiply. The way that I have it written here, it needs to be something that I multiply. So instead of saying divide by 2, I can say I'm multiplying by 1/2. A growth factor of 1/2 would tell me the same thing as divide by 2. And if I have it written that way, I can write out my function. I have y equals my start value times my growth to the power of x. If you don't believe me, let's plug in a value and see. If I plug in, let's try plugging in 2. If I plug in x equals 2, let's squeeze it in over here, y equals 1 times 1/2 to the power of 2. Well, I know my exponent rules. This tells me y equals 1 times 1 squared over 2 squared. I get y equals 1 times 1/4. So I get y equals 1/4 when x is 2. And that matches. My function is correct. So I can write a function for exponential growth. When it's growing each time, it's multiplying by 2. So I have a growth rate of 2. When I am decaying, I have values that are getting smaller. I have that growth that's between 0 and 1. I'm still multiplying, but I'm multiplying by a value between 0 and 1, so I show decay. Just jumping back to that vocab, you don't need to rewrite it, but I have that idea now of exponential growth and exponential decay. What this looks like on a graph then, this is from Desmos, and Desmos is going to be your friend in this chapter here. Remember, to get to Desmos, you go desmos.com, and this is just desmos.com/calculator, and you can type in these functions, and I'll show you at the very end how you can type them in and even have a table pop up where it'll give you values. But if I type these in here, I see 4 different functions. The first one in green, f of x is 1/4 to the power of x. That's this one here. I have g of x is half to the power of x. That's this blue one here. I see that idea of decay. They're getting smaller and smaller and smaller. Well, the other two, I see growth. For my red one, I see y equals 2 to the power of x. And then as that a value, or as the b value increases, my line gets steeper. Just like as I get a fraction with a denominator that's larger and 1 on the top, I get steeper. So you can play with this. If you type these in on Desmos, you can type in y equals ab to the power of x, and it'll ask you if you want sliders. And so you can put in a slider and you can slide a up and down and see what happens to the change. You can slide b up and down to see what happens to your graph. And I think this is a really interesting idea, especially if you're struggling with this. Head to Desmos or shoot me a Teams chat and I'll show you how to get there. So now let's practice with this. I'm going to graph the functions and identify the domain and the range. So for the first one here, I have it written in function notation. F of x, which I know is the same thing as y, equals 3 times 2 to the power of x. So what I see here is I see the 2 pieces, my a and my b. In this case, a is telling me my y-intercept, so I know that when x is 0, y is going to be 3. The one in blue, the b, is my growth factor, so I know that as I change each step for x, I'm going to grow by multiplying by 2. So in my next box, 3 times 2 gives me 6. 6 times 2 gives me 12. I know that the inverse of multiplication is division, so if I want to go the other direction, I divide by 2. I get 3 over 2, and then I get 3 over 4. If I plot my points here, I can start at -2 and then 3/4, so that's going to be just below 1, somewhere in there. My next one, -1 and 3 over 2. Well, 3 over 2 is 1.5. Then I have 0.3, 1.6, and 2.12. Listen here, let's do one more just because we've got some space here. If I double again, I get 24. Well, on this here, 3.24, that's going to be off my table already. I can see that my growth is rapid. When I connect the dots here, I see my curve, my exponential curve for growth. If I'm identifying the domain and range, I need to think about what those 2 terms mean. My domain tells me about my x values. My range tells me about y. So my domain for x, I can go all the way to -infinity for x, and I can go all the way to +infinity. So my domain for x is all real numbers. And this symbol here, that R with an extra slash, I'll write it again. That tells me all real numbers. You can use the symbol or you can write out the words, all real numbers. My range, well, if I look at my y values for my end behavior here, as x increases, y increases. So it goes to +infinity. But as x decreases, I see a space that my line will not cross. There's that invisible line on the x-axis that my function will not cross. So my range for y is all positive values. Y has to be greater than 0. Well, now let's try it again. This function g of x looks very similar to f of x, but this time I have -3 and a growth factor of 2. So that tells me that I have -3. But this time, rather than using that idea of growth factor to fill in the boxes, let's plug and chug. So I want to know when x is -2, what is y? So let's plug it in. I get -3 times 2 to the power of -2. I can type that in on a calculator. I can use what I know, and I find out that it's -3/4. If I do it again for -1, I get -3/2. When I plug in 1, I get -3 times 2 to the first. Well, that's just -6. And then 2, I get -3 times 2 squared. Well, 2 times 2 is 4. 4 times -3 is -12. If I plot my points here, I can see that I have -2, -3/4, -1, -1.5, -2, oops, sorry, 0 is at -3, 1 is 6. When I put in 2, I get out -12. Well, let's do one more here, since we've got some space. If I plug in 3, I get -24. Again, I'm off my chart already. If I'm thinking about domain and range, my domain, again, is going to be all real numbers for x. But my range this time, my y values will always be negative. So y is less than 0. But I want to think about comparing those two functions when I had 3 times 2 to the power of x, and now that I have -3 times 2 to the power of x. So I'm going to jump over to Desmos, and I'm going to plug in those two functions. When I do that, I see that f of x, the red one, and then g of x is the purple one. We can notice a few things about this here. If I were to zoom in, I would see that neither of these functions touch each other, or they never touch each other. They both approach 0, but never reach it. And I can notice that it's a reflection, that it's just the opposite for every single y value as it was in the original function. Interesting stuff here. So now let's try again. This time I'm looking at a growth factor of 1/2, which if I think about my definition here, that growth factor is going to be between 0 and 1, so I should expect to see decay. Same two parts as before. I have my y-intercept and my growth factor. So a y-intercept of 2. A growth factor of 1/2 tells me that I change by multiplying by 1/2 each time I step down my table. So 2 times 1/2 is 1 times 1/2 is 1/2. If I'm working backwards, instead of multiplying by 1/2, I'm going to multiply by 2 or divide by 1/2. When I do that, I get my table here, and so I can fill in my values. I have -2, +8, -1, +4, 0, 2, 1, 1, and 2, 1/2. I can connect the dots with a nice curve. And again, I see that I'm approaching 0, but I don't reach it. If I were to write the domain and range, the domain is that idea of all real numbers. My range, my y values are always greater than 0. I have that invisible line, that asymptote at 0. Well, now this one's a homework problem here. Homework problem number 7, I think it's on the back side. Yeah, homework problem number 7 on the second half of the worksheet looks like this function here. But what we just did is we just had h of x, let's rewrite it, let's go with blue. I had h of x was equal to 2 times 1/2 to the power of x. This time, the piece that's changed for j of x is now I'm adding 5 at the end here. So I want to know how that's going to shift my graph. Well, let's ignore this column that has h of x for a second, and we're going to try plugging in values to figure out what j of x will equal. If I plug in -2 into my function here, I can grab a calculator and do it. If I plug it in, I get 2 times, let's get my calculator to work, 2 times 1/2 raised to the power of -2 plus 5. If I plug this in, I find out that I get 13. If I do the same thing, now I'm going to plug in -1. Well, this time I find out that the answer is 9. When x is 0, well, I get 2 times 1 plus 5. When x is 1, well, I get 2 times 1/2 plus 5. When x is 2, well, I get 2 times 1/4 plus 5. If I look at these values for j of x here, I should notice something about how they are different from h of x. This piece here is h of x. All I did was add 5 to it. So I shifted up 5 units on my graph. 8 plus 5 gave me 13. 4 plus 5 gave me 9. So my graph here will look like, let's graph it in blue so it matches our blue here. When x is negative 2, y is 13. No, it's negative 2, 13. When x is negative 1, y is 9. When x is 0, y is 7. When x is 1, y is 5.5. And when x is 2, oh no, when x was 1, that was a mistake. When x is 1, y was 6. When x is 2, y is 5.5. When I see this here, I want to think about the domain and range again. Well, my domain is going to be all real numbers for x. But my range, I see a new invisible line that my function will not cross. My range is my y values are always greater than 5. That shift also shifted the invisible line that my function will not cross. So when I have addition at the very end here, it's shifting my graph up and down. And so let's take a look on Desmos at what this looks like. When I plug them in here, I have the original h of x is green. It's that first green one here. I can trace over it a little bit. Oof, that's a bad trace. The green one is h of x. And then j of x is that one in purple. I shifted it up 5 units. And I can do the same thing if I shift it up 10 units or if I shift it down. So now I have the idea of y equals my exponential function, y equals a times b to the power of x plus c, where a is telling me the y-intercept, b is telling me the growth factor, and c is telling me the vertical shift. I'm moving it up or down on the y-axis, shifting it up and down. So now you can go ahead and get started on the homework. The worksheet is on Teams. If you were in class today, you received a copy. This is some challenging stuff, but one thing that can really help you out is if you head to Desmos, you can use the calculator. This is at desmos.com/calculator, or if you just search Desmos, you'll be able to find it. And what you can do is you can type in the function. Like this one here, that is homework problem. Let's see, where's my homework? That one is homework problem number 4. If I type into the box, I type y and, let's not do yellow. Yellow is hard to see. Into that box there, I type y and then underscore 1. It gives me the y sub 1 equals, so well, then I just type in my function, 2 times 1/3 to the power of x. And it'll graph that red line for me. The next thing I want to do is I want to insert a table. So I click on that plus button that I see right there, and it'll say table. You want to make the headers at the top of your table be x and y1, or whatever you've called your function here. You can call it y1, you can call it f of x, whatever you want to call it. Make sure that it matches the output here, should match the output here. And then you can type in your values for x that you want to know what the output would be. On the homework, I suggest that you use -2, -1, 0, 1, 2. I put in the 0 because you need to have a 0 for each of them, but you can choose other values, but those ones are going to be the most useful values to graph on the graph that's given. But if you're curious, you can type in other values. This table will match your graph, so it can help you out when you're filling these in. Rather than plugging and chugging using a calculator yourself, you can start to use some of these digital tools to help you out. Make sure that you get this assignment done and submitted on Teams, and we will continue moving forward with Chapter 7. Thanks, guys.